Okay, thank you for the introduction. You can hear me, right? Okay. Actually, I'm a bit of an outsider here, I suppose, because while this is the FPGA Developers Forum, I'm not yet, I think, an FPGA developer. From when I started the PhD, I'm trying to become, but I cannot use yet the title, I suppose. But why I'm here? I'm here to present a field where FPGA, in particular RFSoC systems, are extremely useful, and where FPGA developers are extremely needed. So I will start with a brief introduction on quantum computing, and in particular with superconducting quantum computing. That's the field I'm working in, and where RFSoCs find the most, when RFSoC systems are used. Then I will present my work, what I did in the master, that is Qibosoq, that is actually a software for using RFSoCs, and then something about the future development hoped for the project that will be something more firmware related. So what about quantum computing? We come from very different backgrounds, so let's start with what a quantum computer is. The idea is to stop using a bit that actually encodes very little information and start using a qubit that can encode potentially infinite information. And then it's supposed to behave like a quantum system, so a lot of quantum phenomena can be exploited. And a quantum computer is controlled in a very different way than a standard computer. Every qubit is represented there as a line, is subject to gates, logical gates, where the hardware implementation is in general much more complex and depends a lot on the platform. So usually physicists or quantum computing engineers or whatever, they don't think about the hardware implementation because they can consider just a more abstracted layer. Why is it interesting? Because at some point this guy in the 90s, Peter Shor, found a way of writing an algorithm, mathematically demonstrated, to beat any factorization problem. Like classically, this is a problem that scales exponentially, and so we based, like the majority of our cryptography is based on factorization problems that is more or less unsolvable classically. While with quantum, we can solve it in a very easy way. Now, we have quantum computers. Why this isn't yet been used is because we are very limited in, for example, the number of qubits. Current devices have 100, 200 qubits, while we will need thousands of qubits for more complex algorithms like this. But we are working on that. And also there are many other applications. Like the initial idea of quantum computers started for quantum simulations, because what better of a quantum system to simulate a quantum system? And there are many algorithms that are being used and are already being tested with real quantum devices to simulate molecules, now small molecules, but could be much larger, and then also lattice systems, new materials, and things like that. Then we have quantum machine learning that is expected to provide advantages both for scalability and speed with respect to standard machine learning. And in general, many other applications. From this list, I should add also quantum sensors, like the use of qubit as detectors. That is actually the field that I'm working in. And this is a map that I stole from a YouTube channel. It's the map of quantum computing. There are a lot of stuff here. There is a lot of stuff here. And that's the main thing, that it's a field where no one actually knows where the real advantage will come from. So many things are being tested, and probably the majority of them will end up with nothing, with no real advantage, but maybe some application will get one. And there are now, for now, also very different platforms. Like a qubit is defined as a two-level system. So we can build two-level system in very different ways. Like with photonics, it's very easy. You take the two polarization of a photon, and then you have a qubit. Obviously, you have to be able to control these qubits, to entangle more qubits. And so it's not so easy, but we can do at least different tests with different platforms. I was with superconducting circuits because at my university we had an experience with that. What is the peculiarity of like a superconducting quantum computer is that it's built as a circuit. So you can configure it and design the circuit as you want with the parameters that you prefer. This is like a basic circuit for a quantum computer. The idea is to not use like a standard LC circuit that provides a harmonic Hamiltonian, but to use something that is a Josephson junction that works at superconducting temperatures like 10 millikelvins. And you can build an harmonic oscillator. So you can limit yourself to the first two levels, and then you have more or less a two-level system. This is like a circuit that we designed at our university. It's a fully controllable qubit and can just be printed and controlled. About control, how do we control superconducting qubits? Sending pulses, like voltage pulses that are fairly short, so for some nanoseconds to some microseconds, and are modulated with a high-frequency tone. So high frequency, I mean from 5 to 10 gigahertz, more or less. And that's like where an FPGA can be interesting. Okay, we have like for a single qubit, we may have multiple lines. And this is also important because in a standard system, like without the use of FPGA, it becomes very fast, very complex. This is just the scheme for a control of a single qubit. And it involves 3 arbitrary waveform generators, 2 local oscillators, some IQ mixer for up and down converting. And all of this system is problematic because it's complex, occupies a lot of space in a lab, and it requires calibration, and it's obviously not scalable because this is for 1 qubit. For 100 of qubits, it's unimaginable. For 1,000, even more. So what can we put inside an FPGA? For now, there are multiple companies that actually put more or less the arbitrary waveform generators in an FPGA and sell it, but they still have the arbitrary waveform generators that work in baseband. So they need up converters, local oscillators. Why do they do this? Because it's probably easier. But the solution that the quantum community is currently analyzing is the RFSoC board solution. Why? Because we need speed, we need a very high sampling rate, we need simplicity also in the system. We need a lot of configurability because every year we develop a new technique of building a qubit, a new type of design that requires some different kind of control. So we need also to understand, to have a system that can be configured. And we need cost effectiveness because, for example, commercial solutions obviously are very expensive. So we use RF system on chips that were very well introduced this morning. So I will not spend time here. Okay, the difficulty here comes in the development of firmware. That clearly, as you all know better than me, it's not easy. There are some projects, very few projects around there, some of proprietary. So they are closed source and they are from companies that sell a product. And there are a couple of projects that are open source, open firmware. So we started to use QICK, that is developed at Fermilab. And they provide, using Pink, a firmware. It's open source, although not open actually to collaboration, and a first-level software in Python. Something that is peculiar to QICK in respect to the other solutions is that the QICK firmware is based on a single processor, a single time processor, that can be coded in an assembly language and instruct the different channels, so the different DACs and ADCs for the control of qubits. This was probably easier to start with, but then became a problem, an issue, because a single board, like the ZU216, the evaluation board from Xilinx, can control up to 5 or 10 qubits. But then to scale it, you need more of these boards. And to synchronize them and instruct the board to behave coherently at the same time, it's not so easy. They are now building and beta testing a second a QICK 2.0 that should solve this, but it's still under beta testing. And then the QICK works at a pulse level and not a gate level. So it doesn't work with logical gates, but with low-level gates. So someone that knows how a superconducting qubit works can use QICK, but someone that it's just considering to write quantum algorithms cannot, because it's limited to low-level applications. So we built, like during my master thesis, Qibosoq. So to be like a bridge from the firmware and low-level software to the final user, because again we have to simplify. Qibosoq is a layer in between and more or less abstracts a lot of the low-level stuff that is more related to the firmware of QICK, so in particular like the assembly language, the register assignment part of QICK. And also integrates Qibosoq, the QICK supported boards, into the Qibo framework. So basically, the Qibo framework is composed of multiple libraries in Python that are supposed to be a full stack framework. So from simulation, CPU simulation, and GPU, multi-GPU simulation, to deployment of algorithms with a platform that can be hardware independent, or hardware agnostic. So can support currently both commercial solutions and Qibosoq and so RFSoC solutions. And one, okay, this is like a map of the Qibo framework, but okay. We tested this system against commercial solutions. So this is a speed benchmark with different experiments that are used to calibrate and characterize a qubit. And the RFSoC-based solution was, in general, considerably faster, in particular while considering circuits. And not only faster, but also these are, again, some experiments used for calibrating qubits, but also reached the same level of quality for a fraction of the cost. And now, okay, Qibosoq is being used. I developed it at the Technology Innovation Institute, and it's being used there at my university in Bicocca, and some places in Italy around in NFN are using it, as well as someone in a group in the University of Tokyo. What is the hoped future development, and what should I do in the future, and why I'm learning FPGA development is to detach Qibosoq from QICK, in part to surpass some of the problematics that QICK has, but also to try to build something more that QICK didn't. It's not trying to be. So for now, the QICK development is based at Fermilab, and it will also be like this. But I think it's important to provide a way for people with no FPGA background to in some way configure the firmware or like configure the FPGA depending on their platform, on the specific platform. So depending on their number of qubits, depending on their type of qubits. So okay, one possible solution would be something about partial reconfiguration, but already today and yesterday there were a lot of nice talks that provided other ways. So for example, from C or C++ to potentially configure an FPGA without needing to without the need of a real FPGA developer, since the overlap between people that know how to control a quantum computer and how to develop an FPGA is, as you expect, very small. And with this, thank you for the attention, and I hope it was not too boring. Thanks.
Questions, comments? So I guess I can start with one. I see you also use RFSoC. If I remember correctly, this morning we had a talk, RFSoC possible application for astrophysics, and they were quoting $10,000 for a chip. You're here saying that it's very cost effective, and you're cutting down cost by 10. Are you using a similar price?
Yeah. Like that's U216, for example, that can control up to like 7 qubits in some designs. Costs more or less $15,000. And in respect to the current commercial solution, is a cut of 10, because the current commercial solution are extremely expensive because there are like 3 companies that build and sell these things. So, and obviously this is a big problem for like university laboratories or stuff like that. Yeah.
Okay.
Thank you very much for the talk. Very nice effort. How much scalable is this? I mean, you have an RFSoC with multiple channels, right? And the readout is per RF channel. It's divided by frequency, right? So how many qubits will you be able to control with that technique? I mean, what's the best that can be done?
Okay, well, it depends a lot on the design of the chip. So usually you need one drive line for every qubit, and the readout can be multiplexed. So if the qubit is of the chip is designed well, usually you can use a single readout line for readout of 5 qubits, for more or less. But I mean, then with the 216, for example, so it's generation 3 RFSoC, you can multiplex much more than 5 channels. Because you have like a large bandwidth of 10 gigasample per second, right? So potentially it's very scalable. But at some point you for sure need to use multiple evaluation boards, because like 7 qubits is not so much. Thank you.
More questions? Well, I have another one actually regarding just computing in general, quantum computing. You show a very nice plot, I guess, with a bunch of different applications, right? And I was like, what do you think is the most promising one?
I don't know. That's a very difficult question. I would say that quantum simulation is where I suppose that there will be some real advantage, because it's and it's also extremely important for like pharmaceutical real interesting important applications that are now kind of stuck because of these problems that are exponentially growing in size. And then also like the cybersecurity part, that is like the idea of building an encryption layer that mathematically and physically cannot be breached, is something that many companies and countries are investing a lot into. So,
Thank you. No more questions. I think we're closed. Thanks again, Rodolfo, for this very nice talk.